termination. As you can see, it's an entire different jargon. They are telling some shutdown act, shutdown complete, and something like that. So looks like this side it is 3 packets, and this side it is 4 packets overall, going to and fro. And we can again verify this shutdown act and all that in this capture as well. So let's see if we can get anywhere those sequence of packets. Okay, you can see their SAC, yes, shutdown act, shutdown complete, something like that. So this looks like 2 connections. Okay, so this is one connection getting complete, and this is another connection getting complete. And as I said, if I do some more R&D, maybe I can take an extended session. This time I just want to limit it. So from the look of it, you can understand this is what exactly happened with SCTP, because we cannot just like that adopt just because it has some advantages over TCP and UDP. And see, you should understand this is not as simple as the way we adopted towards CIDR the moment we found issues with class based IP subnetting. Okay, so then the NAT came, the NATing came later. It is not done as a part of IPv4 standards, it is just a band-aid fix. So the entire concept of NAT itself is a band-aid fix, so that you can have a separation between private IPs, private subnet, separation between private IP subnets and public IP subnets, public IP networks. And then you can actually extend the internet addresses so that every device, whatever it connects to internet, doesn't need to have a dedicated public IP. So the whole concept of NAT is highly revolutionary, but it is not done as a part of the initial standard. And similarly, the entire CIDR, which stands for classless interdomain routing, it itself also kind of evolved, and then now we can see subnetting, supernetting and things like that. So no more it is strictly class based when it comes to public IP networks. Okay, so they are subnetted whichever way it is possible, so that we can have enough address space to share across hundreds of connecting devices or servers in the internet. So that's what it is. So same way we cannot do something in this case because it is complicated when it comes to transport layer. It has the other challenges to deal, so it is not so easy and not like sort of natting. We quickly found a solution and then try to adopt. It is not something possible in the case of SCTP. So this is one of the kind of limiting factor. So the whole multi-homing lost traction, and then recently again it started picked up, and now with the emergence of SD-WAN networks and stuff everywhere, they try getting this sort of multi-homing stuff, so that you can have multiple internet networks, you can spread your traffic across multiple networks and things like that. So again this is gaining traction, and also people what they want is they want a reliable connection shared across multiple WAN links and things like that. So again now it is gaining traction, and hence yet another thing which got evolved is this MPTCP itself. The MPTCP, as the name says, it is an extension of TCP, so that you can have multi-path TCP. Again the idea is to support this entire or address this multi-homing requirement. So you can see there SCTP is like this, and what I managed to get is I got this source. This is an sample SCTP server client. So I tried compiling. I'm getting this compilation error. Looks like some library we need to install, and what we can do is it is showing this header file error. So looks like I need to install some library. So let me install this libsctp-dev, and this again says how alienated is this SCTP stack is, because if it is quite prevalent and used everywhere, then this should come by default in this Ubuntu install, but that is not the case. Okay, so let me install this. And then try to recompile this source code, sctp.c. in SCTP test.c. So I just commented. What I do is I uncomment and then we compile. So you can see there it got compiled, and the author says to do this ln command server and client. Let me do that, and let me run the way he suggests. Okay, SCTP server and then SCTP client, and then we run also parallelly a Wireshark capture. In localhost, and then run this client. Yeah, you can see there there is this SCTP protocol transaction, and it's a very simple thing. You can see there the initial connection has happened, and in this case it's a very simple socket code. It's not something we are sending a HTTP traffic, unlike this downloaded capture. So here you can see there in the data he is sending some 15 bytes, which is just this bunch of bytes over here, and then they are shutting down the connection. As we saw there, it is just a shutdown ACK, and then shutdown complete is the sequence, which this side it looks somewhat like TCP, but the terminology or this jargon is different. And for this data you got a SAC, so it is just a one packet, so we got a SAC, just again like a TCP ACK. And in this case for connection it is sending this 4 packets to and fro, so totally 4 packets like this. That's what is that 4-way handshake jargon is actually, which is again little different than TCP. So what I do is I share this GitHub link, and you too can download and compile, and then if you want to do some research, perhaps you can do on this code. Of course it is not written by me, but I'm saying actually. So this is what it is. So the whole idea is you get the multi-homing as a part of the transport layer itself, and this is a good approach, because fundamentally even TCP has lot of things went inside TCP congestion algorithms. Again, some people who are not convinced, there are a lot of algorithms which are supported, and things happens, and I often see every time someone doing a PhD, sometimes they do a research in the TCP congestion algorithm, then they invent their own algorithm, and then they eventually push it to the kernel mainline, and we will find it in the mainline. Okay, so that happens all the time, but here it's a complete different path, because here it gives an opportunity to define your own transport layer technology, and you can completely do from ground up, and even this congestion control, everything you can define by yourself. So SCTP is a good approach, but again the compatibility is the thing. But when it comes to multi path TCP, it's a complete different approach. And if you go here, again we can search where this is positioned in the Linux kernel source. So if you go here in the net folder, you can see there MPTCP is there, and since the name itself says MPTCP, this is not going to be yet another transport layer protocol, so you can't find any other IP proto TCP stuff over there. So it should be just an extension over existing TCP. So if you kind of put this entire thing in a perspective, let's imagine you have a server and you have a client. So as the multi-homing thing is mentioned, if you take two cases, one is SCTP way and one is MPTCP way. Okay, so in the case of SCTP, what we can do is we can have this multi-homing like this. Assume these two systems, let's imagine this is one PC 1 and this is another PC. They are connected directly with bunch of Ethernet cables like this. Okay, so that these two cables emulate two internet connections. So for this system you have this network. Let's assume this is 192.168.1.1 and it does not have any router. So this is, say for instance, 1.2 and this is 2.1, I mean 192.168.1.2, and this is 2.2. okay, so something like that. So everything is /24, so it is 24-bit regular subnets. okay, so everything is a normal regular subnet. So in this way they are connected, and now you can see if you establish any regular TCP or UDP, what happens, the traffic will either go, suppose you run a server socket and client socket. okay, so what happens is this will go either this path, and it will reach and it will utilize only one path. So this cannot be a multi-homed network. okay, either it will be like this, or based on your metric it will be either this path it will try to prefer and it will use. And this is what happens everyday basis. Actually this is not any special configuration or a special topology. This happens sometimes on day-to-day basis. See, I tell you, suppose you have a laptop. The laptop has two internet connections. Let's imagine I have a Wi-Fi router. In fact, not to imagine, I really have a Wi-Fi router at my home. So what happens is laptop will connect via Wi-Fi network like this, like so. But at the same time, I can also have this wired connection connected to this laptop. Although in my home I don't do this way. In my home actually I have connected another Wi-Fi router like a client, something like this, and this connects wirelessly and laptop connects wirelessly, and this laptop has another wired cable which connects to this Wi-Fi router. To this Wi-Fi router, all my servers are connected in this wired network, because I cannot run a wireless port to those servers actually. So this will be like this, and this is my entire lab. It is actually so something like this. See, this is the perimeter of my lab network, versus any home devices, any this CCTV cameras or smartphones. Everything can connect to this router, which is getting actually the internet connection. So this gets the internet connection, a fiber. So from there it is a Wi-Fi hotspot. okay, so from there my laptop I can use, and when I turn on this router, the laptop will get additional IP and stuff. So even now you can see here libconfig, you can see that this is the wired network, this is the wireless network. The moment I switch on, this becomes like a multi-homed system. So which is why I'm saying you may find this type of pictures in the internet whenever you search about IP multi-homing. In fact, it is very easy to set up, because it is nothing but in a lab like setup you can do something like this. okay, so that's what is IP multi-homing. So this is nothing but this, and in fact I can turn on my this router. So once it turned on, what happens is you can find the IP address assigned to this USB to Ethernet port. okay, so the moment it gets assigned, you can see here, this is my 3.x LAN subnet. This is my LAN subnet. So Wi-Fi port will have this 3.x subnet, and this wired subnet is this 1.x subnet. I'm sorry, I think it is 0.x subnet. Yeah. So we wait for a while, and we should see the successful DHCP. You can see there 0.115. okay, so this is a 0. subnet, and the router address is 0.1, and this is 3.1. so that's what it is. So you can see there. okay, so this is how it is, and you can see that even now I can try doing a multi-homing, and effectively the packet should get shared between this router and this router. Of course they won't get two internet connections, but my laptop thinks it has two internet connections. But in my case, what happens is all the packets will get any internet going packets will come over here, and from there it will take only this path. okay, so that's what happens. But my laptop thinks it is multi-homed network. But here is the catch: when you do this route command, you can see the metric clearly states right now, although using the wired network is a bad idea for internet, the internet traffic is going to go through this link. So now it is going to take a longer path. It will go here, it will go here, then it will leave this router. So this is what happens because it thinks wired network is faster than Wi-Fi network. Hence, it has set this default metric this way. But actually, if you see, I prefer wireless as a first preference than the wired network in my home in this scenario. But may not be the case in case if you connect this laptop onto your office network, and in case the laptop has both connections, okay, wired and wireless, then that may not be the case. Or otherwise, I can also do one thing, eliminate this whole thing. I can actually eliminate this whole thing like I have it in my old house. I can have a switch here and connect this wired network of this router LAN port to this, and this I can connect to the laptop. Then it is fine. It can prefer this wired network because the packets will go to the switch, from the switch to this router, and then it will leave here. So hope you got an idea what you can do when you need something like a multi-homed setup. So hence I am saying you have a PC, you have another PC, you have something like this. Now see, when you do SCTP, the regular TCP, as I said, it will go from here to here, and from server to here. It is not going to choose the other alternate path. It will be either of one channel. Hence I gave this entire example. So it will be either this channel or that channel. So it will be not both together. But in the case of SCTP, if you can do that, then what happens? The packets can split between these both ports, and both can communicate in this way. So this happens in socket level. Okay, so this is what it is. But in the case of MPTCP, the context is completely different. It is actually doing is one flow, it is splitting into two subflows or multiple subflows. I mean, not two subflows. You can have this multi-homing with any number of connections. So in the case of this is as I said, this is in the case of SCTP. So let me put it here, SCTP. So this is in the case of SCTP, but in the case of MPTCP, once again, as I said, the multi-homing, it can have any number of networks like this. Okay, you may have two wired ports, two LTE ports, all connected, all are up, or anything is down, the other connections are up. It can be any such possibilities. Okay, but in the case of MPTCP, it is completely different. You have a regular TCP stuff going on between this TCP client and server, but this flow will get split into multiple subflows actually. Okay, something like this, and then it will be carried forward, and that's what happens with MPTCP part. Again, here it will get these subflows will get converged into a single flow. So hence, if you search MPTCP subflows, you get pictures like this. You can see there you have the regular TCP scheduler and splitting them into subflows, and then you have a different queues, and then leaving multiple NIC cards or any network ports. It can be wired NIC card, it can be even LTE as well. So it can be any multiple internet connections. But this is not strictly the case of SCTP. Okay, this is something happens with MPTCP. So this allows us to use the same internet without any changes whatsoever to send this MPTCP traffic, because the routers in between all the IP routers or ISPs, whatever they see is regular TCP traffic. They won't see any different IP protocol like SCTP. And hope, if you are not aware, sometimes an ISP may tune up UDP better than TCP. So in case you have any UDP VPN links versus TCP VPN links, UDP VPN links tend to go faster than TCP VPN links. Hence, don't ever choose TCP as your VPN transport. Instead, always prefer UDP. Okay, hope you got the point. See, what I'm saying is, assume you are doing a VPN architecture and you chosen a transport protocol. If it is UDP, it will go much faster than TCP. The reason is sometimes these intermediate ISPs, most of them try to prioritize UDP better than TCP. So what happens in the case of SCTP? Okay, so SCTP is not well used, so nobody cares, and I don't know what happens if you use SCTP like traffic across internet. Of course it can go, but the issue is we don't know what is the sort of priority you get and things like that. So again, they may actually prioritize TCP better than this something unknown SCTP and hence you may get a different quality of service as you use SCTP, because again it is not widely adopted and widely used. So this is also a issue. So hence an MPTCP like stuff is much preferred than something like this. But again, MPTCP, if you closely observe, as you write a regular socket code, you don't need to do much. I mean, it is the regular TCP inside the kernel. It is getting split into subflows, but may not be the case with SCTP. SCTP, in fact, I hope you can add 2 IP addresses in the socket connection, bind them, and then send to connections from the socket level itself. So you are doing that split from the socket level itself, but not the case with MPTCP. Okay, so again I was searching about it. Let's see, we can find any clues about it. Yes, you can see there in this they are showing some product. It is not any regular Linux commands, it is some product, and what they are showing is, let me increase the font size. You can see what they are showing is show SCTP connections. This is a command in that product. Looks like when you do that, it shows this local addresses, and it also shows this association and stuff. So this clearly says you can actually do from socket level. Okay, this is not something possible with MPTCP, because it is actually a single flow. It is splitting into multiple subflows, and then it is sending across the internet. Hence it's more of a workaround on regular TCP, and the moment you enable a kernel with MPTCP capabilities and things like that, assume your remote server is also MPTCP capable and your local client app is MPTCP capable. Okay, then you can start actually communicating with multiple subflows of a single TCP connection or a flow. Okay, so it is one connection getting split into multiple subflows, but in the case of SCTP you can fundamentally do from socket level itself. But again, I am not sure about the other intricacies. Let's imagine one of the connection gets cut, how SCTP handles and stuff. Again, I am not did any R&D like that. Perhaps I may do some test setup in my VM lab and then do some R&D, and then perhaps may cover in the future episodes. So this is what it is. Hope now you got an idea about multi-homing. And multi-homing, in this context we are discussing about IP subnets or IPv4 stack level or IP level or network layer level, not the L2 level. And whenever you do anything like that in L2 level, it is to be called better as some sort of bonding or something, because you are bonding bunch of L2 networks and assigning a common network address or IP address to that. And in the case of IP bonding, you may have like this, and every connection may have, every link, obviously it will have its own MAC ID. This guy will have its MAC ID, this guy will have its MAC ID, and this guy will have its MAC ID, this guy will have its MAC ID. But in the case of L2 bonding, that is not the case. You may have a common MAC ID as well to the entire channel, and then a common IP address to that entire channel, and things happens. So again, there are different types in the bonding. You can have failover or stuff like that. Okay, so that is there in the L2 jargon. So if you are well versed with L2 jargon and coming to this multi-homing thing, there are a lot of other intricacies like this, and you have lot of approaches. Some succeeded in the event of due course of time, some didn't picked up, although it's been in talk in the past, but SCTP never picked up. In the case of MPTCP, it is gaining traction in a unique way. It is not actually getting used in its true intended purpose. Its true intended purpose is, whenever you use a smartphone, assume you have both data connection and as well as Wi-Fi connection. Effectively, you see, it's a multi-homed device. So let's imagine you have a smartphone, okay, connected to both LTE, and it may have multiple SIMs, so it may have multiple LTEs also, and then it is connected to Wi-Fi network. Okay, now you think, whenever you browse internet, whenever you watch any video, stream any content, it should effectively spread the load on all these links. And let's assume you don't have Wi-Fi, then the smartphone should able to use both LTE links and get combined internet speeds. And this is what exactly we need, multi-homing. And in this case, we can see the actual usage of MPTCP, because it can connect, say for instance, to YouTube, split a single TCP flow into multiple subflows, or TCP connection into multiple subflows, and it can download at a faster rate than what it is possible with single LTE connection. So this is the whole thing. Hence, it is not unfortunately yet used in this intent, but instead what it is getting used is, it is getting used in multi-WAN routers, so that a multi-WAN router, okay, this is a multi-WAN router. So currently it is mostly used in this context. Okay, so multi-WAN router may have multiple WAN ports, wired WAN ports, and it may have WAN facing LTE ports. So if you ask me, I generally use the term WAN in general. People generally, what they confuse is, they just use the term as WAN if it is a wired port, and they tell it is 4G network, it is not a wired port. But I prefer using the term as WAN facing ports. It can be anything. So it can be LTE, say this is LTE2, LTE1, and this is a WAN 1, and this is WAN 2. So it's a pakka multi-WAN router. So in the case of multi-WAN router, of course, this side you have the LAN port, and of course it has a Wi-Fi capability as well. So in the case of multi-WAN router, you can connect your regular home or office over this side. So you have a regular home or office network, okay, connected to this multi-WAN router, and then it can bring in this MPTCP stuff over here, and then it can take this, do some sort of a VPN stuff, and then put it inside the encapsulated path, encapsulated stuff, VPN stuff, and then it can create multiple MPTCP subflows. So which can go, these subflows of course can go across all these WAN facing ports. Okay, so that's how currently it is getting used. So this is MPTCP. It's just not MPTCP alone, as many gets confused. It is MPTCP with some custom VPN stuff. Okay, so that remotely there is some sort of a server you deploy in a cloud or somewhere. You have a server with public IP, something like that, and all these guys, all these subflows will go there, and then they converge there from this router, and from there again it will be connecting to this backend internet actually. So hope you can understand, it's not actually used for its true intended purpose, as it is used in a completely different way it is getting leveraged. Okay, so this is what is currently happening, but its true intention is, these are the various use cases. You can have a regular router, or you can have a regular system with multiple WAN facing ports. Even a simple laptop with combo of Wi-Fi and wired ports is a multi-homed device. And the class, yet another good example is this everyday smartphone. it can have multiple SIM cards, so you have multiple LTE connections, and it can have even Wi-Fi connectivity, and you can combine if you wish. And MPTCP should make that possible every time you browse anything in the internet, and if it is coming from a TCP source, we can leverage this MPTCP. Of course, you cannot do that for UDP based applications. But again, if you go with this approach, since here a third party router is doing, let it be TCP, UDP or ICMP, whatever it emerging from this network will get tunneled inside this MPTCP, and outside the internet it will be always a TCP subflow, which is the MPTCP subflow, versus whatever coming from this home office is going to be this multiple protocols, actually UDP, and this is TCP. So this is what happens. Okay, so hope you got the entire big picture, and now we compare what happened to SCTP. What happened to SCTP is a complete different architecture, it's a complete different approach, and you need to change the whole internet on a grassroots level, and that is not going to happen due to the compatibility, backward compatibility and things like that. Hence it never picked up. So hope this video is as usual useful and insightful. If you have anything to discuss, be in touch via mail or post your small queries in YouTube comments. Thanks a lot for joining me. Stay tuned. Have a nice day. Bye bye.